Hi, thanks for clicking me. I'm Claudio Codella from the rcetri Observatory, and in the next slide we will talk about protoplanetary disks, of course, and more specifically we will talk on H2CS emission. What's the context? The context is a star forming process. So the process that led a cloud transforming into a star and its planetary system. And the chemistry was also evolving. The chemical composition was also evolving from simple molecules to prebiotic and eventually biotic chemistry. So the class 0 stage has been extensively observed and sampled, chemically sampled by several programs using single dish and interferometers. And we found plenty of lines and molecules. Those are just examples. And the nice thing that I would like to stress is that once we zoom in, observing on solar system scale, this is, for instance, in observation of a protostar, it says 212 on a 10 AU scale, we see that the chemical richness is coming, at least in this case, from the protostellar disk. So what's the next step? Going from class 0, that is roughly 10 to the 4, maximum 10 to the 5, beyond 10 to the 5, so entering into the class, late class 1, early class 2, evolved class 1, so we are talking about objects of less than 1 mega year. Why is important? Because it's the next step to start with, and because ALMA showed that during that stage, planets can already form. So we report here observation of the ALMA-DOT project that concerns observation of this kind of sources, young disk around class 1 objects in Taurus using several molecular tracers. So, okay, we understood why protoplanetary disks, why chemistry, but why sulfur-bearing chemistry? Because there is a huge problem. We do not know which is the main sulfur-bearing molecule on dust grains, okay? So there are plenty, that's a long-standing problem since last century. And of course, the first try were regarding H2S, that is the most obvious molecule, is resembling water, okay, for oxygen, and or CS. But those species have not been detected in ICES, so still this is a problem. What H2CS has been observed in star-forming regions, in protostellar stages, but what about protoplanetary disks? So, protoplanetary disk has been observed commonly using CS and SO, but if we are focused on H2S and OCS and H2CS, we have the following results. One image for H2S, no images for OCS, and 2 images, 2 disks for H2CS. This is a nice paper by Romain Legal, 2019, and followed by the paper by Loomis and collaborators, 2020. And here we come, and we report 2 observations in 2 other disks, HL Tau, okay, the queen of this conference, and the so-called IRAS04302, the so-called butterfly disk. So we start with HL Tau, that we see the H2CS is clearly coming from a disk a disk with the outer radius of roughly 140. We will see that this number is quite important once discussed at the end. The column density is around 10 to the 14, centimeter to the -2, once assumed conservatively a temperature between 20 and 150 K. And the nice thing that if we use the great, fantastic image by Booth and Eiley of 13C170322, we can infer a rough estimate of H2CS abundance that could be quite useful for modelers, that is around 10 to the -14. If we go to the kinematics, we see that this ring is also rotating, not surprisingly, and is rotating as, for instance, shown by other species like CS 524 here below. So so far, so good. What about the butterfly disk? Okay, so the picture is not so clear like HL Tau. If we go through the moment 0 or moment 8 map, again, we see that the emission is, in any case, confined in the inner 115 AU. The peak column density is, again, 10 to the 14 centimeter to the -2. But everything is more clear if we add kinematics. We add kinematics, we clearly see that this stuff is rotating, okay, like, for instance, observed in H2CO by Linda Podio recently. So everything is consistent with a rotating ring, and indeed, if we go through the channel maps, we see that we can find, we can speculate, if you want, a relationship that is the velocity that goes as the radius, that is the classical kinematical signature of a ring. So everything is consistent with a rotating ring also in the butterfly disk. But the plus of the vertical, the butterfly disk, of course, is the vertical distribution. So if we take the equatorial plane z equal to 0 and we go towards the upper or lower side, so towards the west and the east sides, we see that once taking into account different signal to noise, the H2CS emission is consistent vertically with the CS and the H2CO that has been traced using brighter emission. So it looks that all the three species are coming from the same molecular layer. That is consistent also with the fact that these three species in the gas phase are formed using small hydrocarbons. A step ahead can be done asking the help of our friends working on chemistry, and in particular on the friends of University of Torino that derived the binding energies for the first time for an extended crystalline ice of H2CS and CS and formaldehyde, but that's another story. And that's is being done for the first time for an extended ice, and they derived also an estimate for amorphous ice that is probably the most plausible configuration of dust that you can expect there. I'm not entering into detail because there is no space for that, but to make a long story short, these findings imply that thermal desorption occurs for temperatures larger than 50-80 Kelvin. So it means that the H2CS observed at radii larger than 100 AU are not injected due to thermal desorption, but indeed by non-thermal processes. So plenty of details cannot be reported here for sake of clarity and for a question of time. What I can just say is that that's just a first step of a long trip from protostellar to protoplanetary to cometary object to understand our chemical origins. And with this message, I leave you. Thanks for your attention.